It's generally not recommended to use a multi-wire branch circuit or MWBC with fluorescent lighting because of the possibility of harmonic distortion and neutral overload. Fluorescent lighting fixtures that use electronic ballast produce harmonic currents. Harmonic currents are frequencies that are multiples of the fundamental frequency, which is 60 Hz in the United States. These harmonics are able to distort the voltage waveform. This distortion may then create problems for other electrical devices and pieces of equipment. In a multi-wire branch circuit, the neutral wire is responsible for carrying the sum of the return currents coming from both of the circuits. When fluorescent lighting is used on a multi-wire branch circuit, the harmonics may lead to the neutral current being higher than the ampacity of the neutral wire. If this happens, overheating and even a potential fire hazard could occur. To avoid these problems, it's recommended to use separate branch circuits for each set of fluorescent lighting fixtures. Each individual circuit will then have its own neutral wire. Doing so will prevent both harmonic distortion and neutral overload. The National Electrical Code, or NEC, doesn't specifically prohibit using multi-wire branch circuits with fluorescent lighting. However, it does require that the neutral wire be sized appropriately. It needs to be able to carry the full load of both circuits. This includes the harmonic currents that are produced. Meeting this requirement can mean using a larger neutral wire than what would normally be needed for a non-harmonic load. While not explicitly prohibited, it's generally not a good idea to use a multi-wire branch circuit with fluorescent lighting fixtures. Using separate branch circuits for each set of fixtures will be a safer and more reliable option. The issues arise primarily due to the nature of electronic ballast commonly found in fluorescent lighting and their impact on the electrical system. Now let's delve deeper into the technical aspects. Firstly, understand the fundamental principle of a multi-wire branch circuit. A multi-wire branch circuit shares a neutral conductor between two or more ungrounded conductors that have a voltage between them. These ungrounded conductors are connected to different phases of a power source, such as a 120/240 volt single-phase system or a 208 or 480 volt three-phase system. Ideally, in a balanced system with purely resistive loads, the neutral conductor carries only the difference in current between the ungrounded conductors. This allows for efficient use of conductors and reduces the overall wiring cost. Secondly, consider the effect of electronic ballasts. Electronic ballasts, unlike older magnetic ballasts, use electronic components to regulate the current flow to the fluorescent lamps. While they offer advantages such as higher efficiency and reduced flicker, they also introduce harmonic currents into the electrical system. Harmonic currents are currents with frequencies that are integer multiples of the fundamental frequency, such as 120 Hz, 180 Hz, and so on. Thirdly, let's analyze the problem of harmonic distortion. Harmonic currents do not cancel out in the neutral conductor of a multi-wire branch circuit like fundamental frequency currents do. Instead, they add up arithmetically. For example, if each ungrounded conductor is carrying 10 amps of harmonic current at the third harmonic frequency, the neutral conductor will carry close to 20 amps of harmonic current at that frequency. This can lead to a significant overload of the neutral conductor, even if the fundamental frequency currents are balanced. Fourthly, the implications of neutral overload are significant. Overloading the neutral conductor can cause it to overheat, which can damage the insulation and create a fire hazard. Additionally, the increased current flow can cause voltage drops in the neutral conductor, leading to voltage imbalances in the connected loads. This can affect the performance and lifespan of sensitive electronic equipment. Fifthly, the NEC addresses these concerns by requiring that the neutral conductor be sized to carry the maximum unbalanced load, including harmonic current. Section 220.61 of the NEC provides guidance on calculating the neutral load for household ranges and electric clothes dryers, which can also generate harmonic currents. For fluorescent lighting with electronic ballasts, the NEC requires that the neutral conductor be sized to carry the maximum load served by the circuit. Sixthly, to mitigate the risks associated with harmonic currents, several strategies can be employed. One strategy is to use dedicated branch circuits for fluorescent lighting, with each circuit having its own neutral conductor. This prevents the harmonic currents from adding up in a shared neutral conductor. Seventhly, another strategy is to use harmonic filters to reduce the amount of harmonic current generated by the electronic ballast. Harmonic filters are passive or active devices that are designed to block or reduce the flow of harmonic currents in the electrical system. They can be installed at the individual lighting fixtures or at the main electrical panel. Eighthly, it's essential to specify and install lighting fixtures with low harmonic distortion ballasts. These ballasts are designed to minimize the generation of harmonic currents. They typically meet industry standards such as ANSI SATI 2.77, which sets limits on the total harmonic distortion of electronic ballasts. Ninthly, when designing and installing electrical systems with fluorescent lighting, it's important to carefully consider the potential impact of harmonic currents. Use appropriate conductor sizing, overcurrent protection, and grounding techniques to ensure the safety and reliability of the electrical system. Tenthly, consider a practical example. Suppose you have a multi-wire branch circuit serving 2 circuits of fluorescent lighting, with each circuit drawing 10 amps of fundamental current and 5 amps of third harmonic current. If the neutral conductor is sized only for the fundamental current, it may be overloaded by the harmonic current. In this case, it would be necessary to increase the size of the neutral conductor to accommodate the harmonic current or to use separate branch circuits for each set of fixtures. In conclusion, while it may seem cost-effective to use a multi-wire branch circuit for fluorescent lighting, the potential risks associated with harmonic distortion and neutral overload outweigh the benefits. By using dedicated branch circuits, harmonic filters, and low harmonic distortion ballasts, you can ensure a safer and more reliable electrical system. Always consult with a qualified electrician to determine the best approach for your specific application and to ensure compliance with all applicable codes and standards. It's worth delving into specific NEC articles to reinforce this understanding. NEC Article 210.4 discusses multi-wire branch circuits, and while it doesn't explicitly forbid their use with fluorescent lighting, it mandates that the neutral conductor be sized appropriately to handle the maximum imbalance load. This is where the consideration of harmonics becomes crucial. NEC Article 220.61, as previously mentioned, provides guidelines for calculating neutral conductor loads, including provisions for nonlinear loads that generate harmonics. While this article primarily focuses on household appliances, the principles can be applied to other types of loads, including fluorescent lighting. NEC Article 300.13b addresses the continuity of the neutral conductor in multi-wire branch circuits. It requires that the neutral conductor not be broken when devices are removed or replaced. This is to prevent a situation where the unbalanced load is forced to flow through other paths, potentially overloading them. NEC Article 310.15 and related tables provide guidance on conductor ampacity. When sizing conductors for multi-wire branch circuits with harmonic loads, it's essential to consider the directing factors specified in these tables to account for the increased heating effect of the harmonic currents. NEC Article 400.5 addresses the use of flexible cords and cables. While not directly related to multi-wire branch circuits, it's important to ensure that any flexible cords or cables used in conjunction with fluorescent lighting are properly rated for the voltage and current they will carry. NEC Article 410 covers lighting fixtures, lamp holders, and lamps. This article provides requirements for the installation of fluorescent lighting fixtures, including provisions for grounding and bonding. Proper grounding and bonding are essential for minimizing the risk of electrical shock and for ensuring the proper operation of protective devices. It's also important to understand the concept of total harmonic distortion, or THD. THD is a measure of the amount of harmonic content in a voltage or current waveform. A high THD indicates a significant presence of harmonic currents, which can lead to the problems discussed earlier. The Institute of Electrical and Electronics Engineers, or IEE, Standard 519 provides recommendations for harmonic control in electrical power systems. This standard sets limits on the allowable THD levels in electrical systems and provides guidance on how to mitigate harmonic problems. In addition to the NEC and IEE standards, there may be local codes and regulations that apply to the installation of fluorescent lighting. It's important to consult with local authorities to ensure compliance with all applicable requirements. When selecting fluorescent lighting fixtures, look for products that are certified by a reputable testing laboratory such as Underwriters Laboratories or UL or Canadian Standards Association or CSA. These certifications indicate that the products have been tested and found to meet applicable safety standards. Finally, remember that electrical work can be dangerous. Always follow safe work practices and consult with a qualified electrician if you have any questions or concerns. By understanding the potential risks associated with multi-wire branch circuits and harmonic currents, you can ensure a safer and more reliable electrical system for your home or business. Always prioritize safety and consult with qualified professionals to ensure that your electrical installations meet all applicable codes and standards. Also consider the specific type of fluorescent lighting you are using. Different types of fluorescent lamps and ballasts can have different harmonic characteristics. For example, some electronic ballasts are designed to minimize harmonic distortion, while others may generate significant harmonic currents. The type of fluorescent lamp can also affect the harmonic content of a current waveform. Some lamps, such as compact fluorescent lamps, or CFLs, may generate more harmonic currents than others. Before installing fluorescent lighting, it's a good idea to consult the manufacturer's specifications to determine the harmonic characteristics of the lamps and ballasts. This information can help you select the appropriate wiring methods and overcurrent protection devices to minimize the risk of harmonic-related problems. Also remember to check the voltage rating of the fluorescent lighting fixtures and ballasts. Make sure that the voltage rating is compatible with the voltage of the electrical system. Using fluorescent lighting fixtures or ballasts with the wrong voltage rating can damage the equipment and create a fire hazard. When installing fluorescent lighting fixtures, be sure to follow the manufacturer's instructions carefully. This will help ensure that the fixtures are installed correctly and safely. Proper installation is essential for minimizing the risk of electrical shock and for ensuring the proper operation of the lighting system. It's also important to consider the ambient temperature where the fluorescent lighting fixtures will be installed. High ambient temperatures can reduce the lifespan of the lamps and ballasts. If the fixtures will be installed in a hot environment, such as a warehouse or factory, consider using high temperature rated lamps and ballasts. Also consider the location of the fluorescent lighting fixtures. If the fixtures will be installed in a damp or wet location, such as a bathroom or laundry room, use moisture-resistant fixtures. Moisture-resistant fixtures are designed to prevent water from entering the fixture and causing a short circuit or electrical shock. When replacing fluorescent lamps, be sure to use the correct type of lamp for the fixture. Using the wrong type of lamp can damage the fixture and create a fire hazard. Also, be sure to dispose of used fluorescent lamps properly. Fluorescent lamps contain mercury, which is a hazardous material. Do not throw fluorescent lamps in the trash. Instead, take them to a recycling center or hazardous waste collection facility. Furthermore, consider the use of LED lighting as an alternative to fluorescent lighting. LED lighting is more energy efficient than fluorescent lighting and does not generate harmonic currents. LED lighting also has a longer lifespan than fluorescent lighting, which can save you money on replacement costs. When selecting LED lighting, be sure to choose products that are certified by a reputable testing laboratory. This will ensure that the products meet applicable safety standards and performance requirements. In conclusion, using a multi-wire branch circuit with fluorescent lighting is not strictly prohibited by the NEC, but it is generally not recommended due to the potential for harmonic distortion and neutral overload. To avoid these problems, use separate branch circuits for each set of fluorescent lighting fixtures, use harmonic filters, or use LED lighting. Always consult with a qualified electrician to determine the best approach for your specific application and to ensure compliance with all applicable codes and standards.